And okay, now we are ready. So remember from last time that we were studying the flow of a vector field. Now, because today we only have 1 hour, so I'm not going to continue with the flow. We will do that tomorrow. So in the meantime, I want to see something related to vector fields. And tomorrow, when we have the 2 hours, we will retake the, the flow of vector fields. Okay, then so let's start. Today we're going to define the Lie bracket. So what is this? So we have a manifold, and then remember that we have the collection of all of the vector fields on N. We denote it like this. And we have seen, I just decided to write it as sections. Remember that we have seen this particular vector bundle, the tangent bundle. So there are smooth sections of the tangent bundle. So this is a vector space over the reals, and it is an infinite dimensional vector space. Moreover, we have seen that we can multiply a vector field by a smooth function. So in fact, this set is a module over the ring of smooth functions. But today we're going to see an additional feature of the set of vector fields, and we are going to show that it's in fact an algebra. We are going to define, so to speak, a product of vector fields, which is called the Lie bracket. Okay, so let's try and motivate a little bit about this product. So consider two vector fields, x and y, and also two smooth functions. Remember that a vector field is a derivation, right? So then we have the product rule on functions. So let's see what happens when we take two vector fields. So first remember, if I take a vector field and a smooth function, think of this as just one function. The vector field applied to a function is again a smooth function, okay? So now, here I'm just saying exactly the same. This is a vector field. This is a smooth function. So I have a function. Now let's see what happened with the product, in quotes, of two vector fields. So we would like to see if this is a vector field. And what do I mean by a product? I mean something like this. This is a function. But we would like to know if it's a vector field. Right? So I have this. So it makes sense. So I mean, hold on. You have this. What is the meaning of this? Is this vector field applied to this function, okay? So this is in fact a smooth function. And now I would like to see if this is a vector field, meaning that if it's a derivation, that's why I have two functions here. Okay? So, first of all, a vector field, well, I mean, y is a vector field, so I apply the chain rule, the derivation of y, right? So that's why I have y of f times g plus f times y on g, okay? I'm using the fact that we have a derivation. I'm missing here a parenthesis. Let me write it here. Okay. Now, the vector field is linear, so I'm using the fact of linearity on the vector field x alone. I have that. And then, again, I'm going to use the fact that x is a derivation because I'm applying this to this product of functions. So we will see what happens now. So I have this. The first part is only this. X is a derivation, and I have it like that. The second part, again, x is a derivation, but now apply to a distinct product of functions. Okay? A derivation, you have here xf, and then f alone. Okay, now, I'm going to put together the first term and the last terms, because that's basically what I would be expecting if I would like this to be a derivation, right? It would be f, this apply on g, and then g, this apply on f. So I'm just moving this and this on this side. And what I have in green is what I would only expect for this to be a derivation. So this is something that does not vanish, and that's why I cannot say that xy is a vector field. So no, it's not a vector field, because it needs to satisfy the product rule, Leibniz rule. And I have this, which is non-zero. So remember, the whole idea is to put, to make the set of vector fields into an algebra to define a product. And if I do it the naive way, it doesn't work because this is not a vector field. This is not only equal to this. I have something else. Well, so that doesn't work, but what works is the following, and that's the definition, and that's going to be what we will call the product of two vector fields, and it is usually called the Lie bracket. So I'm going to take two vector fields, and I'm going to obtain a new vector field. And this Lie bracket is defined as follows. On the smooth functions, is basically the commutator. X times y minus y times x. And in fact, this is a vector field. It lies in here. Okay? So for that, you only have to consider the negative of this. So this, in fact, is a vector field. I'm not writing it down, but we can write it down here. So no. Up to this point, any questions, Salvador?
No, not yet.
Okay, so let's see that this is a vector field, by that meaning that it satisfies the Leibniz rule. Sorry, this is wrong. I want the Leibniz rule, so I need a product here. So what is this? This is x, y on f times g minus y times x on f times g. Okay? And let's just replace what we computed here. Remember that this is this, right? So let's replace this. So I have, so basically the first part is Leibniz rule, x, y, right? This is the first part, let's see. Right? Now, the second part is just basically the combinations of x, y, and f and g with a plus. It is commutative, so let's put this. Oops, this is wrong. It's g. Plus x, g, y, f. Okay? I just wrote down the first part. Now, you have to tell me what to write for the second part. So I have a minus. So we need to replace x by y. Right, Salvador? We just replace x by y. Okay, so here I will get y, x, f, g, plus, oh, sorry, minus. Everything has to be minus. Minus f And now yx g. And then a minus yf x g. And a minus yg times xf. Oh, and this is, I don't know why I wrote equal. This is not an equal. Okay. Right. How can I get eraser? Now. Okay. You see that the last 4 terms cancel out? Well, I'm sorry. Yeah, I mean,
In each line, right?
Yeah, exactly. The 2 and 2, yes.
The last two.
Last 2 and last 2 of each line. Right. So this with this, and this, and I only get those 4 terms. And so you see, the first, this and this, what is it? It is the Lie bracket of x, comma, y applied to f times g. And the other one is f and the Lie bracket x, comma, y applied to the function g. Okay? So in fact, we have a vector field. So indeed, this is a vector field. So this is the Lie bracket. That's the definition of the Lie bracket. Sometimes in notation, we will just write it like this, okay? So it should be a familiar object to you from the algebra point of view, like the commutator of x and y. Now, there is also a geometric interpretation of the Lie bracket. And it is given in terms of the flow of the vector field x and the vector field y. So I'm not going to go over this. We will leave it for tomorrow. But I'm not, like the Lie bracket, it has some geometric interpretation. It is measuring something. Well, I mean, from the point of view of algebra, you know what it measures. I mean, the commutator of 2 elements is 0 when they commute. So basically, the Lie bracket is measuring the commutator between x and y, if they commute or not, or they don't commute. That's the whole idea of the bracket. Now, I'm going to give you a few properties of the Lie bracket. The first one is that it is antisymmetric. And this is just by the definition, right? Because of this sign. So the Lie bracket is antisymmetric. Now, the other property is this one here, how it behaves with functions, okay? For instance, if f and y are constant functions, remember that a vector field applied to a constant function is 0. So if f and g are constant functions, this is 0, this is 0, and we have something like this. So basically the constant functions, we can just move them out of the bracket. But in general, that's not true if f and g are not constant. The third property, this is fundamental. This is called the Jacobi identity. The whole idea is to take twice the Lie bracket, right? So you put x, y, and z, and you do a cyclic permutation. So now y, x, and z, and then c, x, and y. So you do a cyclic permutation of the three vector fields, and what you get is 0. So this relation is called the Jacobi identity. Okay, now I'm not going to give you a proof of this. You can do it by your own. It's just the same algebraic manipulation that we did here and here. Basically, that's the knowledge that you need to prove that proposition. Okay? Know that x and y and the bracket is a derivation, and you can prove these two properties. The first one by definition, but these two are just algebraic manipulations of the differentials. Nice. So work it out on your own. If you have any questions, so get back to me. Okay, I would prefer to move on. Now, from the first property that the Lie bracket is antisymmetric, we have our first computation of the Lie bracket. That the Lie bracket of x with itself is 0. Okay? So we have our first computation of the Lie bracket. Here is any manifold x, any vector field. The Lie bracket with itself is always 0. Okay, now, so the reason that I skipped this is I prefer to do examples, and so that you will know actually how to operate the Lie bracket. So because that's the goal of this example, I decided to go with something very easy, just R2. Our manifold is R2. We have coordinates x and y. And so let's compute the Lie bracket of a pair of vector fields. And I'm going to write this. I decided not to put specific functions. So just remember that f and g are smooth functions. Oops, I forgot here, sorry. So they depend on x and g. And basically, I mean, we are going roughly to give an example of, or a proof of the second, of number 2 of this, right? With a particular x and a particular y. Okay? So, okay, so the first thing to do is just definition of the Lie bracket. So here, nothing new. Okay? Now, I mean, the whole purpose of this example is to make you understand this, how to manipulate this info. So look, the whole idea is we should think of this, and this has functions. They are functions. And this is the vector field. This is the vector field. I did this on purpose. I didn't put here any function phi. So I just want you to get used to this notation. Okay, so now let's use the fact that this vector field is a derivation, and also this one. Right? So here is only this. I have this with this function, and then this applied to this function, which is here. Right? Now I need the second term. You have it there. This derivation of this product. You have it here, and you have it here. Okay? Salvador, is this clear?
Yes.
Okay. Now, here is where, so, I mean, you should think of this as a, well, first of all, si tengo que, dame un minutito. Sí, mil disculpas, pero es justo porque la computadora está fallando, me la dan mantenimiento. Okay, now, so here, I mean, you should know that, okay, this is a vector field, a function and ddx, a function and ddx. That's a vector field. Ahora sí, Omar. Ah, Sí, la compu me dio problemas. Me mandaron otra y también tiene problemas. Estoy en un dilema. Perdón. Okay, so I mean now, Salvador, you tell me what do you see and what is next? This is not the final answer because this doesn't look like a vector field. What can you say about it, Salvador?
Maybe we can change the order of the partials.
Right, exactly. Of these two, right?
Yep.
And so you know that in order to do that, you need your functions. Whatever function you plug in here or here, that function must be at least C2. But because we are working on smooth manifolds, all of our functions are C infinity, so they commute. So exactly as you said, this is going to cancel with this. And so the final answer, this is what we're computing, is this. And you see, I mean, this is a vector field, right? You see, this is a smooth function, and this is ddy, a vector field. This is another smooth function, and this is the vector field. So, is this clear, Salvador?
Yes.
Now, here also I would like to point out the following. Again, why it is good to talk about C infinity and not CK. Because if F and G are in CK, what you get here is no longer in CK. You see, with this, you drop the regularity. So you will get this type of vector field. So this is again what it is important that we have C infinity. We can take derivatives and the regularity does not change. There will be C infinity. Nice. So this is something that I really wanted you to understand. There are always two aspects: the theory, the abstract theory, properties, how to move objects around, but there's also some other aspect which are computations. You should be able to do computations with no problem and understand every step. Nice. Okay, now again, I just needed on an easy example. All of the features here are the most relevant. So if you're given vector fields in Rn explicitly, you can compute the Lie bracket with no problem. Nice. Okay, so at this point, what we have on the infinite dimensional vector space of vector fields, we have an additional structure. It is an algebra. The algebra is given by the Lie bracket. So that's our product of two vector fields. So that's why, well, this is what is coming next. we have seen a Lie group. A Lie group is a manifold G where the product and the inverse are smooth functions. That's a Lie group. So maybe for you, let's justify this because we know what a group is. So maybe you will think, okay, Lie has to do with having the smooth structure, smooth inverse, a smooth product. But later, when we were looking at this, I told you that this is the tangent space at the identity. This is a finite dimensional real vector space. The dimension of this vector space is the same as the dimension of the group. And I told you that this vector space is called the Lie algebra of G. And well, you might say, okay, because this is a Lie group, so it's good to call this Lie something. But I mean, we need to justify this. So far, here, the only algebraic structure that we have is the one of a vector field or the reals. We have no product. We need to define the product of two vector fields to justify this name of algebra. Okay? Bueno. ¿Sí? Salvador, mil disculpas, que no ha sido una buena semana. Pero bueno. Okay. No, sí, no está muy bien. Okay, so this is something that we need to justify. We have it for the set of all vector fields of the Lie group, but this is something different. This is the tangent space. So we need to justify that. And that will come not, I think, next week, but it is very much related to the Lie bracket that we defined. Okay? Let me give you a very, very simple example, the one that we have studied. We have seen that this is a Lie group. In fact, this is an open set. Remember that? Now, in an open space in Rn, the tangent space is this. But we identify this with the set of n by n matrices. So This is in the algebra. What is the bracket? So you take two vectors. But here, remember that two vectors are matrices. So on this space, this is the same, the commutator. This is the product matrix minus, right? So that's what makes this into an algebra. This is the product, the commutator of matrices. Now, G is non-singular matrices, but the tangent is the set of all n by n matrices. So, I mean, this is a particular, but we need to define in general what is the algebra structure on that tangent space to a Lie group. Okay? Salvador, any questions?
No, right.
Right. So remember that today we have to we end early, and we will move to the other talk.
Bien. No, para